Hello everyone, my name is Mike and I'm going to share with you 10 techniques that I have for improving your group delay measurements on frequency converting devices that have embedded local oscillators. So I'm talking about things like this, MyTech satellite block down converter. This is a device that takes a 20 gigahertz signal in and down converts it to about 1 gigahertz using an internal embedded local oscillator operating at 18.75 gigahertz. I want to measure the group delay of a device like this, and I want to share with you 10 techniques I have for making that measurement as easy and accurate as possible. Now, of course, for my measurements, I am going to use a Rohde Schwarz ZNA vector network analyzer. We introduced this network analyzer to the market about 1 year ago, and we focused on making it the best instrument possible for frequency converting measurements. In particular, I'm going to use option K9, which is our two-tone technique for measuring group delay on devices with embedded local oscillators. Now, for more information on that option, you can see application note 1EZ81 on our website, which describes this measurement technique in detail, including the equations and everything you need to know. But what I'm doing in this video is going through the different techniques, the different parameters that you can set for the measurement, and we're optimizing those parameters to give us the best result. And we're looking real time at the instrument to see what the effect is as we change each parameter. Now, I have 10 ideas for making improvements, so that's 10 different videos, one for each idea. In this video, I'm on idea number 7, which is to use LO tracking to figure out what's going wrong when the measurement doesn't look right. So LO tracking is a feature that we have that will help us figure out what's happening if the local oscillator is at a different frequency than we expect. And that's entirely possible, that when you connect this device, you think the local oscillator is at exactly 18.75 gigahertz, but in reality, maybe it's a little bit off. And in fact, for this demonstration, I've intentionally made sure that my local oscillator is off in frequency from where I expect it, so we can see how this option works. Okay, so let's look real time on the instrument at how this is done. And for this, I'm going to use my GPIB Command Explorer tool again to create 2 channels, and I'm going to calibrate both channels exactly the same way. And then I'm going to use this LO tracking feature in one of the 2 channels to show you the difference in real time. So let's start by presetting the instrument. Let's launch this GPIB Command Explorer tool, and let's open a file called number 7 LO tracking. This will set up the 2 channels. It'll ask me to connect the calibration mixer, which I already did. So we can calibrate the 2 channels, and then it will activate LO tracking in one of the 2 channels. Now, in this case, the calibration mixer, there's not going to be an error with the LO because the LO is being provided by the network analyzer itself. But when we connect to the device under test, that's when we will see the advantage of using this option. So let's connect the input and output cables to the device under test. Now, I just want to remind you that up to now, we've optimized the resolution bandwidth setting of this measurement, and we've selected a 1 kilohertz bandwidth. And I'm also going to tell you ahead of time that the error, I detuned the LO in the device under test, and I detuned it by just over 1 kilohertz. So that means the expected tone frequency is going to be on the sideband of our resolution bandwidth filter. And it's going to see some attenuation, and that's going to cause noise during the measurement of the phase of the 2 tones. So that's what's going to create the problem, and this is going to show you how we can mitigate that effect. So let's scale these 2 channels to have the same scale. Let's couple the 2 channels to have the same scale, and then let's bring them down onto the screen, and let's zoom in just a little bit because I can see this bottom channel is actually making a quite nice measurement. So I'm at 300 picoseconds per division, and this bottom channel is reporting that it sees an LO error of 1.1 kilohertz. Again, if we confirm the bandwidth, it's set to 1 kilohertz. So it sees that there's an error in the LO frequency of the embedded of the device that's being tested, and it's correcting for that error numerically in the FPGA so that we can make a good measurement. In the upper channel, everything is the same except this LO tracking feature is not enabled. Now, you find this LO tracking feature by going to the mode key, and there's a checkbox for tracking or not tracking the LO. So in channel 2, it's checked. In channel 1, it's not. That's the only difference between these 2 channels. If I go to channel 2 and I turn off this tracking, then I see a noisy trace just like channel 1. So LO tracking is a way for us to see if the problem that's on the screen is being caused by the local oscillator drifting away from where we expect it in the device under test. Now, I don't recommend that we use this measurement, this technique, during the measurement of our device under test. Instead, I recommend it be used as a troubleshooting tool. So when we see a trace like this in channel 1, we have a way to figure out what's going on. We don't spend our time trying to optimize the IF bandwidth or the tone spacing or any of these other things. Instead, we focus on the fact that, hey, the LO is not where it belongs, and that's what's causing my trouble. And now that I've found this problem, I can then either retune the LO in the device under test so it gets back to where it belongs, or I can update the setting on the network analyzer to say, hey, don't expect it at 18.75 gigahertz. It's really supposed to be somewhere else. Let's actually set the analyzer up to where it's supposed to be. So this is a good troubleshooting technique. It quickly shows us what's going wrong, and it helps us to get to the point where we can make a very accurate measurement of group delay. So this is idea number 7 on my list of 10 techniques for improving your group delay measurements. And in the next video, we're going to go to idea number 8. And I can already tell you, this one is a really good one. I can't wait to show it to you. Okay, I will see you then.